Hi, everybody. My name is Max Gronke, and I'm a NASA Hubble Fellow here at the Johns Hopkins University. And I would like to show you some stuff we've been doing in regards of the destruction and growth of cold gas in hot environments. And we, that's mainly Peng O, who is at UCSB, and me. I guess I don't need any introduction for this kind of audience. We all know that multiphase gases exist on various scales. I'm mainly interested in the scale of galaxies, and in particular how gas is fed to these galaxies and being recycled from them, and how that affects galaxy formation and evolution. But I'm excited to hear more about completely different scales, like coronal rain or clusters during this conference. What all these systems have in common is, as I said, there's multiphase gases, and if we would zoom in on some of these boxes, what we would see is some blob of cold gas, which has a certain number density and a certain size, and this is moving with respect to the hot environment. The hot environment has therefore a certain speed and also a certain number density, and what would happen in such a scenario is that hydrodynamical instabilities would develop and destroy the cold gas on a timescale, which is of order of the Kelvin-Helmholtz or Rayleigh-Taylor timescale of the system. So given by the cold gas size divided by this wind speed times the square root of the overdensity. And if you compare this timescale to the timescale it would take for the wind to accelerate the cold gas, which is again the same fraction of the size divided by the wind speed, but this time times the overdensity, you notice that because in astrophysics we commonly work with high overdensities, that this acceleration timescale is much larger than the destruction timescale. And what that means physically is that cold gas is being destroyed before it can be accelerated to the wind speed. And you see this in this video down here where I show a slice through one of our simulations, and indeed in a few of these destruction timescales, the cold gas mass, what you see in the title, is going down significantly. And that's been a long-standing problem in astrophysics because we see fast-moving cold gas basically everywhere, but what's easily fast-moving is the hot gas due to, say, supernova or AGN feedback. When Peng and I revisited this problem, we thought, this cold gas is not really being destroyed, but instead it's being mixed with the hot gas. And you can compute the properties of this mixed gas following this classic paper by Begelman and Fabian. The temperature of this mixed gas is given by the geometric mean of the hot and the cold temperature, and so is the number density. And these two quantities let you compute the cooling time of the mixed gas, which is longer than the cooling time of the cold gas because this gas is less dense, but not that much longer, only by a factor of 10 or so. And now if you require that this cooling time of this mixed gas is shorter than this destruction timescale, so physically, this mixed gas can cool before the gas supply of new mixed gas ceases, this should mean that the cold gas can survive. Let's put this to a test. Here, I show you the same movie I showed you before. In the upper panel, where this critical ratio is larger than unity, and in the lower row, you see a simulation where this critical ratio is smaller than unity. And indeed, while in the upper simulation, the cold gas is being destroyed, in the lower one, the gas mixes and cools and collects in this tail, and we end up, in fact, with more cold gas than we started with, as you can see in the title. We can plot this in a bit more quantitative way. Shown here is the cold gas mass as a function of time. And these are the two simulations I just showed you before. And if we populate the parameter space with different overdensities and different values of T-cool mix over T-destruct, you see that overall our criterion seems to work quite well. As a bonus, what is nice is because the cold gas is cooling out of this fast-moving hot gas, what that means is that it's easier for the wind to accelerate the cold gas. And you can see this here where I show you the velocity difference between hot and cold medium as a function of time. And you see that most of these clouds get entrained faster than the fiducial drag time. Focusing back on the survival criterion, T cool mix has to be smaller than T destruct. The left-hand side of this criterion is a function of only the gas properties, whereas, if you remember, the right-hand side depends on the size of the cloud, which means that you can rewrite this survival criterion to a geometrical criterion, which states that clouds larger than some critical cloud size, and I plugged in some numbers here typical for galaxies, which ends up being 2 parsec, only those clouds would survive. That's a prediction of our model. With magnetic fields, here I show you a simulation where I put magnetic fields orthogonal to the wind inside the wind and tangled magnetic field inside a cloud. It's also working, as you can see in this movie here. We end up with more cold gas than we started with. In the lower 2 plots, I show you again the mass, cold gas mass as a function of time. And you see that, for more magnetized clouds, the mass growth is a bit slower. That's expected because magnetic field prevent mixing, and therefore, we have a slower mass growth rate here. But it's not that much slower if you compare it to the hydrodynamic case, which is shown in the black line. And the right plot here is again the velocity difference between hot and cold gas as a function of time. And you see with higher magnetized winds, we get a faster entrainment, and that's because of this magnetic draping. And you can write down what is expected, which is shown in these boxes here. So, it roughly follows what is expected. What I would like to spend more time on is the long-term evolution of the gas. And that is because at first, this is maybe a bit puzzling because, the mass growth rate, as you see here in this plot, seems to flatten out, although the velocity difference, which leads to shear between hot and cold gas, drops. And if, the shear would be responsible for the mixing, also the mass growth rate should drop, but it does not. And the reason for this, you can maybe infer from the movie down here, which this time I show you the cooling emission, a slice through the cooling emission, so where the cooling is happening. And you can see even in this late times when the cold gas is already entrained, there is these interesting waves inside the cold gas clouds, which lead to pulsations, which therefore lead to further mixing and further cooling. So we obtain this large converged mass growth rate, which is a bit puzzling if you look closer at this cooling emission slice here, because you can see that basically all the cooling is happening in this one cell thick emission layer. And that is happening even if we increase the resolution. What we find then is that m dot, the total mass growth rate, seems to be converged, but this emission here is not converged. And that's highly puzzling because, m dot is proportional to your total luminosity, which is your emissivity times your volume. To get to the bottom of this, Brent Tan, who is a grad student at UCSB, he simulated in detail one of these mixing layers. And here you see slices through his simulation box, again, the temperature and cooling emission. And he found results which are consistent with ours, larger scale cloud simulations. So a seemingly converged mass growth rate and the mass growth given by this kind of equation here. But again, this one cell thick emission layer. And the reason for why, the emissivity, is always peaking in this one cell thick layer is easily understood because in his and our simulation, we did not include thermal conduction. And therefore, we cannot resolve the field length, which sets, the width of one of these emission layers. So that's puzzling. Why do we have, m dot being converged, but the emissivity structure is clearly not? The second question I would like to address is, if you look at this equation here, m dot is given by first order by the cold gas sound speed. That's what he and also we did find. And that's strange because, the hot gas surrounding the cold medium can sustain a much larger mass growth rate, namely given by the hot gas sound speed. So why is it that small? And the third question is, how does m dot scale with the cooling time or the cooling strength? And we found this -1/4 scaling shown in the red curve here. But Brandt actually varying the cooling strength over many orders of magnitude, he found that there's this other regime where it follows -1/2, and then there's this transition between these two regimes. These two different cooling regimes, they are not just different in the way m dot scales with the cooling strength, but also morphologically the shape of this mixing layer changes quite a bit. On the left, in this weak cooling regime, you have a lot of this mixed 10⁵ Kelvin gas, which is shown here in white. And I stepped through a fixed simulation here. And on the right, in the strong cooling regime, these two phases, hot and cold phase, they are much more separate. It's a much more multi-phase structure in this cooling regime. Figuring out what's going on there, it was quite hard for us, but we got help from, for us, a somewhat unexpected direction, and that was the field of turbulent combustion. So in combustion, what you do is you mix fuel and oxidizer, and then this burns on a very short time scale. And what we do is we mix hot and cold gas, and this mixed gas then cools on a very short time scale. So these two, phenomena are somewhat related, and you see this here, maybe, if you look at this image of this turbulent flame, it looks very similar to this image I just showed you from the emissivity. And I don't have time to get through all these great results from this very mature field, but I just want to point out this one classic paper from Gerhard Dammköhler from 1940, where he figured that the total burning rate is not given by the laminar flame speed, but the turbulent flame speed. And he also already figured out that there's two different regimes, what he called, a straight, a well-stirred regime, where he saw a straight flame front in his experiments with the Bunsen burners. And then he had another regime where the flame was much more corrugated and the flame front was wrinkled. And he found that these two regimes are separated by this dimensionless quantity given by the turbulent time divided by the reaction time. And later on, people named this characteristic number actually Dammköhler number. And, Brandt also calculated this Dammköhler number for several of his simulations. And you see, it fits quite well. It separates these two regimes quite well. But we can do more. And, now armed with this knowledge, we now know that m dot is given by your turbulent flame speed, and you can just rewrite that as a turbulent diffusion coefficient divided by some reaction time. And the reaction time in this well-stirred regime is nothing else than the cooling time, because gas is well mixed, so it can just cool freely. In the corrugated flame regime, it's a bit more complicated because not all the gas can cool, as you see. There's only a small volume of the gas that can cool. And then it turns out, that this reaction time is the geometric mean of your eddy turnover time times and the cooling time, as stated here. And if you plug this in, you obtain this -1/4 scaling. I don't want to confuse you too much, and maybe that's too much detail, but this one thing I wanted that you can take away from this is that there has been actually experiment by Gulder et al. who also found this -1/4 scaling, which made us quite happy, because their experiments obviously have a much better resolution than our simulations. So returning to these three questions I posed before, I talked a lot about the scalings now. What about this convergence issue? Well, it turns out that this turbulent diffusion coefficient is much larger than your numerical one. And the way turbulence works is that your eddy turnover time increases with scale in a Kolmogorov spectrum, and therefore your mixing is set essentially by the largest the outer scale. That's very similar to a situation what you have when you mix cream into your coffee. To resolve this, what you would need to resolve is the motion of the spoon, the large motion of the spoon, and not the detailed molecular diffusion between cream and coffee. And what that implies is that, conduction doesn't really matter for this problem. So here, Brand actually did include conduction in 3D turbulent mixing layers, and, no conduction in blue, and then higher conduction coefficients. And you see overall the cooling rate, and therefore m dot, is very much the same. And the last question, why is m dot to first order given by the cold gas and not the hot gas sound speed? If you look at this equation out there, it's given by your characteristic turbulent velocity, which is both in these transonic winds, but also in these pulsating clouds, is more or less given by your cold gas sound speed. And that answers these three questions. I'm sorry if that was a bit technical to the end, but there's just three take-home points I want you to remember from my talk. So first of all, cold gas can survive a ramp pressure acceleration process if the cooling time of the mixed gas is smaller than the destruction timescale, or you can rewrite that being that clouds have to be larger than a certain characteristic size. And then, once clouds did survive this acceleration process, they in fact can continuously grow because of these cooling-induced pulsations I showed you. And the way they grow, they follow a certain law, and we think we understand that quite well where this comes from now, because it's backed up by this mature field of turbulent combustion. Thank you for listening.